upbeat, crisp musical intro that fades out.
Okay, take a look at this. This is the regular dodecahedron. With its 12 perfect pentagonal faces, it's just an icon of geometric perfection. You know, it's one of those shapes that just feels right, doesn't it? So balanced, so complete. In fact, its perfection is so profound that entire research papers, like the one this explainer is based on, are dedicated to just pinning down its precise structure.
But here's the thing about this kind of perfection. It isn't magic. It's pure logic. So that leads to some pretty big questions. What are the hidden rules that actually create it? And here's where it gets really interesting. What happens when we take those exact same rules and try to push this perfect shape into a whole other dimension?
To even begin to answer that, we've got to look at the dodecahedron's blueprint. Because in the world of geometry, a shape this perfect doesn't just happen by accident. No, it's the result of following a very, very precise recipe.
And you might think its foundation is, some kind of physical material, but it's not. It's just a list, a precise list of 20 points in space, 20 sets of x, y, z coordinates. That's it. These points are the entire blueprint. If you get them just right, this perfect shape simply emerges.
And baked right into that recipe is a pretty famous number, the golden ratio, or phi. Now, what's so cool here, and what our source material really drills down on, is why it's there. Phi isn't just some artsy aesthetic choice. The paper calls it a structural consequence. What that means is you literally can't build this shape with its perfect pentagons without it. It's a non-negotiable part of the structure. Okay, so we have a list of coordinates. Big deal, right? How do we really know? How did geometers actually prove that this specific recipe creates a truly perfect dodecahedron and not just something that, looks pretty close?
Well, they have this incredibly rigorous, step-by-step verification process. Think of it like quality control for shapes. First, you place those 20 points, the vertices, in space. Then, you connect the closest ones and measure them. If you get exactly 30 edges and they're all the exact same length, you're on the right track. Next, you hunt for closed loops of 5 edges to find your 12 pentagonal faces. And then, here's the final killer test. You have to confirm that one perfect sphere can pass through all the corner points, another can pass through the middle of every single edge, and a third can rest perfectly tangent to every face. If all of that checks out, boom, you've proven its perfection.
And this is where the source material makes a really important point, a critical disclaimer really. They say, look, this is strictly geometric. We are not making any grand claims here about physics or biology or the meaning of the universe. This is a disciplined, focused exploration of pure form, period. So, that discipline is what allows us to ask the next really fascinating question. We've got this verified, perfect 3D object. So, what happens if we take its own rules, its own blueprint, and use them to extend it into the fourth dimension?
Now, the way you do this, according to the source document, starts with a step that's almost shockingly simple. You just make an exact copy. That's it. So now we have 2 identical, perfect 3D shapes ready for the next step. To get them into 4D space, we give every single point a new 4th coordinate. Let's just call it W. For all the points on the first dodecahedron, we set W to -1. For all the points on the second copy, we set W to +1. And just like that, they're not in the same 3D space anymore. They've been separated along a 4th spatial axis, a new direction that we can't see.
And this is such a brilliant way to understand the difference between the 4D reality and what we can actually visualize. The real object is that 4D structure, where all the geometry is still perfect. What we see is just its 3D projection, its shadow. You know how the 2D shadow of a cube on a wall can look all stretched out and distorted? It's the same idea. Our 3D view of a 4D object might look a little warped, even though the thing itself is perfectly regular in its own dimension.
And you guessed it, the source material is super careful to draw that line in the sand again. This is a geometric exploration, a representation. It is not a claim about physical reality or how our brains perceive the world. It's a mathematical what-if game played with logic.
Okay, so this rigorous mindset, this way of thinking, it isn't just for understanding mind-bendingly complex shapes. You can actually use the exact same approach to uncover fundamental laws in problems that seem, on the surface, way simpler.
So let's switch gears. Think about this classic problem. What is the absolute most efficient way to connect 3 points? Let's make it real. Imagine 3 towns on a map. Where should you build a central junction to minimize the total length of road you need to connect all 3? Well, geometry gives us a definitive answer with a strict rule. It turns out, if all the angles in the triangle formed by the towns are less than 120 degrees, the best solution is to build a new central point. But, and this is key, if one of the angles is 120 degrees or more, the shortest path is to simply use that town's corner as the junction. It's a vertex collapse.
And here is the really elegant part. In those cases where you do build a new central junction, the three connecting paths don't just meet at some random angle. They always meet at exactly 120 degrees. This constant, this number, just emerges naturally from the simple logic of minimization. And true to form, the source that lays this out does it with that same intellectual precision. It's not a new force of nature. It's what they call a law of closure, a self-contained, verifiable geometric principle that works perfectly within its own clear boundaries.
Okay, so this all brings us to the big takeaway here, what we can call the geometric mindset. We've looked at a complex 4D extension and a really simple connection rule. On the surface, they seem totally unrelated, right? But they're not. They're products of the exact same powerful way of thinking.
And that method really boils down to 4 key steps. You start with precise definitions. You build a model that can actually be tested and verified. You test it with rigorous, stone-cold logic. And, maybe most importantly, you are crystal clear about the limits of your work, stating exactly what you are not claiming.
Ultimately, the real discovery here isn't a shape or a number. It's a mindset. It's this way of thinking that allows us to strip away all the noise and uncover the hidden, elegant laws that govern the pure logic of space itself.
And that leaves us with a final question to chew on. What other elegant rules might be hiding in plain sight all around us, waiting to be revealed not by a powerful telescope or a microscope, but simply by a clear question and a set of logical steps?